All right, guys, number 26. So here's the situation. I'm going to delete a lot of it. I'm going to take the text away and the picture away because I'm going to need a lot of room to solve this. So basically, this problem starts out by doing a free body diagram for this, they call it a boom. Okay, so here is my boom. I made it bigger so we can see all the forces. And so let's clear everything else. So we're going to make a lot of room to solve this. All right, so what are the forces that are acting on this boom? In fact, here, let me move the boom over a little bit. So we're going to grab this guy. Oops. Grab this guy. Okay, forces acting on the boom. So you got to refer to the problem. So we have an object hanging off the boom here. This is 2,000 newtons. The problem mentions the weight of the boom as being 1,200. So where does that go? Directly in the middle. A little higher. So directly in the middle, we put the weight of the boom straight down. 1,200 newtons. No, that's not straight. Make this straight. Straight down like that. That's a little better. Okay, what else is acting on the boom? If you look at the picture in the problem, we have a rope. We have a rope that's connected like this. And so we're going to call that tension. And then this angle here is 25 degrees. That's a given. And then down here where the boom is on the hinge, there has to be a horizontal force that keeps the boom from slipping. You know, if there was no force there, like if this boom were resting on a frictionless surface, like somebody put a bunch of melted butter down there, what would this boom do? It would slip. It would slide to the left. So there's a horizontal force keeping the boom from sliding, and then there also has to be a vertical force holding the boom up. So the problem wants us to find three things. Oh, and then this is 65 degrees. Okay, the problem wants us to find three things. Find the tension, and then it says find the components of the reaction force at the hinge. So what it means by components of the reaction force is force vertical and force horizontal. And just be aware, force horizontal and force vertical, are they really two different forces? In reality, it's one force at an angle. You know, the hinge exerts a force at an angle. But those would be the components, force horizontal and force vertical. Okay, now, let's put our distances in. So I'm going to do the distances in red. So they don't give us a specific distance. You know, all they tell us the length of the boom is L. So let's draw this in here. So the length of the boom, distances, you always have to have an axis. Guys, is there an obvious axis for this problem? Is there a point that stands out where it's like, oh, it's going to rotate from there? Not really. Where's the best place to put the axis when you don't have an obvious axis? At the point where you have the most unknown forces. Because that way, these guys will not appear in the summing of the torques. Forces on the axis cause no torque. Okay, so that's the axis right there. So now let's put in the distances. You have to have your axis set before you can talk about distances. Okay, so the whole length of the boom is L. To the tension, to this point right here, so right there, they tell us in the problem that that's 3/4 L. This is 3/4 L to there, and then to the midway point to right here, that's going to be L over 2, right? That's half the length of the boom to the middle. So that's L over 2, the whole thing is L, and then to the rope is 3/4 L. All right, so we got 3 unknowns here. If there's 3 unknowns, how many equations do we need? 3. So here are the 3 equations. We are going to sum forces X, sum forces Y, and then lastly we're going to sum the torques. Okay, summing the forces in the X. We have 2 X forces. What are the 2 X forces? Force horizontal is X, and then what else is X? The horizontal component of tension, T sub X right here. Okay? So this is going to be, we're going to go force horizontal minus cosine 25t. Those are the 2 X forces. Sum of the forces equals ma, but is there an acceleration? Nope. So this goes to 0. So summing the forces is not that bad. Okay, in the Y direction, we have 4 forces. We have 1, the Y component of tension, 2, and then 3, 4, right? There's 4 vertical forces. So here we go. This is going to be force vertical plus sine 25t. That's the Y component of tension. Then minus, let's just add these together, right? 2,000 and 1,200 both point down. Just add them together, 3,200. Sum of the forces equals ma. Do we have any vertical acceleration? Nope. That goes to 0. All right, so we have 2 equations done. Now, the third equation, here we need some room. Let's scoot this over. Okay, so now we're going to sum the torques. All right, so sign convention for torque, clockwise, counterclockwise. So which way is tension pulling here? So when you're figuring out clockwise, counterclockwise, you have to know where the axis is. So the axis is down here. So what's tension? Tension is pulling the boom which way? Counterclockwise, CCW. And then these guys here are going to be clockwise. So let's say that counterclockwise is plus, clockwise minus. It doesn't matter. You can do it the other way. It doesn't matter which way is plus or which way is minus. So let's start with tension. Now what's nice here, guys? There's something mighty nice here. It turns out that tension is perpendicular to the boom. How do I know that? Well, look, down here this is 65. So that means that this must be 65. What's 65 plus 25? 90. So that's perpendicular. So that's pretty nice. So what is the perpendicular distance? So when we do the torque for tension, we need the perpendicular distance from the axis up to the force. What is this distance right here? It's 3/4 L, right? 3/4 L is the perpendicular distance to the tension. All right, so first torque, we're going to go tension multiplied by 3/4 L, right? That's the torque for tension. T times 3/4 L. All right, let's go to the next torque. So let's go to the 2,000 here. Now, this is going to be tricky, dudes. Is the 2,000 Newton force, is that perpendicular to the boom? No. So there's one of 2 things you could do. You could either make the tension perpendicular to the boom. You could go like this. Go boom, boom, and then what would this guy be right here? That guy's going to be, so we need an angle here. So this angle in here is going to be what? 65. Just do geometry. So this is going to be cosine 65 times 2,000, right? So then you take, so that would be your force, and then what's the distance perpendicular to that? L, right? So you could do that, or if you don't like that, what you could do is make the distance perpendicular to the force. So drop the force down. Here's the force. And now you can do a perpendicular distance right there. So what's this perpendicular distance going to be? Cosine 65 times L, right? You can either make the force perpendicular to the distance, or you can make the distance perpendicular to the force. It doesn't matter. So let's go minus, let's do what I have set up here. So this is going to be, so the force is 2,000, and then what distance is perpendicular to that? Cosine 65L, right? It's this distance right here. That's perpendicular to the force. Okay. Then last one, minus, okay, 1,200. Drop the force down. What distance is perpendicular to that? Cosine 65L over 2. So this is going to be 1,200 times cosine 65L over 2. The sum of the torques, oh, I'm out of room. What will always be true of the torques? They'll cancel in this class. Okay, so now we got this equation. The L's drop out. The L's cancel. The only thing missing in this equation is what? Tension. So now you solve that for T. It comes out to be 1,470 newtons when you solve that for T. And by the way, guys, this is why we put the axis right here. We stuck the axis right there, so that way this guy and this guy didn't appear in the summing of the torques. Okay, so now that we have T, you plug T in here, and you can get force horizontal, which comes out as 1,330, and then you can get force vertical from that guy. So force vertical comes out as 2,580.